Okay, this is a fairly nice straightforward question to start us off. We have a relatively simple statically indeterminate beam here. So like always, the first task here is to work out the individual stiffnesses of the sub-elements that make up this structure. So that's where we'll kick things off. So looking at member AB, at A we have no rotational resistance, and at B we do have some rotational resistance because the member is continuous over that support and it continues on to C. So for a member like that where we've got rotational fixity at one end but not the other, the stiffness of that member will be 3EI over L. So we'll say K for member AB is going to be 3EI over L. Now that's in contrast to a member that has rotational fixity at both ends. In that case, the stiffness would be 4EI over L. So that's the first thing that you have to be aware of at this early stage in answering a question like this. So we've got 3EI over L, which in this case will be 3EI over 3, which will just be equal to, let's just call it 1EI. Moving on to member BC, we have a similar situation. So K for BC will again be 3EI over L, because if we look at this same situation as the previous member, we have rotational fixity at B because the member flies over support B and is restrained over at A. So that gives us rotational fixity at B. And at C, our member flies over C, but it's not restrained at D, it's a cantilever at D. And so essentially there is no rotational resistance provided by the structure at joint C. So what we would say is KBC is 3EI over L. L in that case is 8 meters, and so 3 over 8 will give us 0.375 EI. Okay, so that's the first hurdle jumped. We have our relative stiffnesses. Now, we don't need to calculate any stiffness for member CD because it's a cantilever and you're not going to distribute any moment into a cantilever using the moment distribution method, and so there is no distribution factor to worry about for that member, and therefore there is no stiffness to worry about for that member. So now we can move on to those distribution factors. What we're doing here is we're going and looking at each joint where there are members coming in, multiple members, more than one, coming in and meeting at that joint. Okay, so the first one of those we meet is joint B. So let's look at a distribution factor for BA. So the distribution factor for BA is simply the stiffness of member BA, which is going to be 1, divided by the sum of the stiffnesses of the members that meet at that joint. So that's going to be 1 plus 0.375, which will give me 0.727. Obviously then the distribution factor for the other side is going to be 1 minus 0.727, which is simply going to be 0.273, because the sum of the distribution factors meeting at a joint must always equal to 1. Now we can look at joint C. So for joint C, we do have 2 members coming in and meeting at joint C, but we'll notice that one of them, the one on the right, is a cantilever, and so the distribution factor for member CD for a cantilever will always be 0, okay, which means that the distribution factor for CB, the other side of that joint, is going to be 1. And that's always going to be the case when you have a cantilever. So just for completeness sake, we'll write that down. So, fixed end moments. Step 3. So let's look at member AB first. So if I sketch out member AB, we have locked joint B, and that's why we have what looks like a fixed end support here. So essentially the substructure we're considering for this fixed end moment is a propped cantilever. We know that that's going to develop a fixed end moment at joint B, and we're going to label that fixed end moment FEMBA, and that is equal to, in this particular scenario, that's going to be WL squared over 15, and that is going to equal 6 kilonewton meters. 6 kilonewton meters. So when we lock joint B, due to the loading to the left of joint B, that is the moment that would develop, as I say, if we locked up that joint. We can now move on and consider member BC, doing exactly the same thing. We can sketch out the structure. So the fixed end moment for BC is going to be the same formula because it's the same type of structure, but this time the moment is going in the anti-clockwise direction, which we will assume to be negative. So the sign convention here for these moments is that clockwise is positive, anti-clockwise is negative. So we will have a negative W, which is going to be 10, times L squared, which is going to be 8 squared over 15. And that will give us a fixed end moment of minus 42.67 kilonewton meters. The last fixed end moment to consider is the cantilever moment, and that's quite straightforward. The fixed end moment that would develop if we locked joint C is going to be a negative 150. Right, now we have all of our fixed end moments. That's essentially our third step nailed down. The next stage is the moment distribution process itself, and the best way to handle this is in a table. It's the most systematic, logical way, I think, to handle this distribution process. So we can go ahead and set that table up now. Okay, so far what we've been doing is just inputting onto this table all of the information that we've accumulated about the problem up until now. So we have our distribution factors and our fixed end moments. Now the actual distribution process begins. So what we do is we look at each of these joints where there's a moment in balance. And so the first one we'll look at is joint B. And we say to ourselves, right, we have a clockwise moment of 6 kilonewton meters and an anti-clockwise moment of minus 42.67. So that means to balance that joint, because that's what we're trying to achieve is moment equilibrium at the joint, because we know that has to be the case in the final solution. We know that we need to add a plus or a clockwise moment of 36.67 kilonewton meters to that joint in order for it to be balanced. Okay, so that's the first thing we say to ourselves. Now, once we know what moment we have to add to the joint to balance it up, then the next thing to think about is how does that moment we're adding get distributed? And it gets distributed between the members meeting at the joint in proportion to the distribution factors for those members. So we're going to take our 36.67 and say 72.7% of it goes into member BA, and that works out to be a 26.66. So let's put the plus in there. And we're going to add the remainder, which is going to be 10.01. So plus 10.01 to member BC. So we've essentially balanced up that joint by adding an additional moment to the joint. Now we can move over to joint C and do the same thing over there. We say, okay, there's an anti-clockwise moment of 150. I need to balance that up. I'm going to balance it up by adding 150 kilonewton meters to that joint. But notice the distribution factors. That whole 150 has to get added to member CB. So we're going to say plus 150. Because remember, member CD is a cantilever, and we can state at the very start of this question what the bending moment is at C, because it's quite easy to work out the moment from a cantilever. So that has to be a negative 150 at the very end of the question. So we can't add anything down here because we know we have to finish up with this 150 at the end. So that's the rationale behind why we have a distribution factor of 1 and 0 at that joint. So we've balanced up our joints, but in doing so, we've added bending moments. Now, those bending moments need to be carried over to the adjacent joints where there is rotational fixity. So if we look at member A, or joint A rather, that's a pin joint, right? So there's no rotational fixity at joint A, and so the bending moment that gets carried over is 0 because there's no rotational fixity at A, it's a pin. Now let's look at carrying over half of our 10.01. We have to ask ourselves, if I was to carry over 10.01, well, I would imbalance this joint again, but this joint is balanced now. And the peculiarity of a joint that is at the root of a cantilever is, in this procedure, once it's balanced at the very start of the distribution process, we leave it balanced. So we're going to carry no moment over because joint C is already balanced. We don't need to play around with joint C anymore. Then we look at this 150 that we added, and that is where we will carry over. So we're going to carry over 50% of that, which is going to be plus 75. So now we have, in doing so, we've imbalanced joint B again. So remember, if C to D was not a cantilever, we'd carry over half of this 10 over to here, and we'd go through a process of rebalancing. But because C to D is in fact a cantilever, the procedure is that we've got to balance it up at the very start of the distribution and leave it well alone. So that's why we carry over 0. So the only thing now to consider is the distribution of this new 75 kilonewtons that is now in kilonewton meters that has imbalanced this joint. So we need to add a negative 75 kilonewton meters in the correct proportions, which will work out to be minus 54.53 and a minus 20.48. Okay. Now, we've already established that the carryover to joint A would be 0. Nothing has changed, so there's no carryover to make there. We've already also said that there is no carryover to make to our already balanced cantilever joint. Okay, so there's no carryover to consider there. So we have essentially completely balanced out our structure. So we're done. We can take our distribution process no further. So at this point, we're going to sum up to determine our final moments at each joint. Just a minor rounding error here. We're always looking for these moments to be the same as each other. And then obviously for joint C, we know that this has to be, we could have said at the very start of the question that that needed to be minus 150, which means that this is also a plus 150 to balance it out. So again, these two figures are the same, and so we're happy. So that is essentially the end of the distribution process. The next thing to consider is how do we use this information in our free body diagrams to fill out the rest of the information we need to complete this analysis.